Hello, my name is Jae Hyeok Kim. Currently in my fifth month of internship at NetVerta under the ATAP program. Today I'll walk through what I've worked on so far, including the accomplishments, challenges, technical insights, and soft skills that I've gained. To give more context about the company NetVerta, which I have worked for last 5 months, the company specializes in mobile computer vision and body scanning, mainly for apparel and footwear fashion industry. Previously, it supplied its 3D scanning technologies and client services like fashion brands app, but now they're expanding into social and e-commerce domain with their own app called VeriFit. I was part of a sub-team within the web team, aka backend team, formed to develop a proof of concept for newly proposed real-time backend infrastructure, something foundational for the company's next phase, such as feature that requires some millisecond latency like mix and match, and well, not to mention to generally decrease the time the system takes to respond to client requests. The mission was to develop a real-time backend system similar in responsiveness to apps like Discord and Slack. We explored modern internet protocols like HTTP3 and web transport, aiming to improve scalability and reduce latency as much as possible. We were at the same time given a very high-level design of the system, and our task was to develop this idea into an actually tangible system and test its performance over the legacy ones. The project went through four phases: initial infrastructure and protocol benchmark environment setup, data collection and visualization, architecture materialization and deployment, and system benchmarking, followed by data collection, visualization, and its evaluation, which is going on right now. I began off by using industry de facto infrastructure as a code or IaaC tool like Terraform and Helm to set up the cloud infrastructure on AWS, including Kubernetes on EKS, secret management via Vault, continuous integration with GitLab, and GitOps with FluxCD. I then created a custom client-server benchmarking tool in Go, implementing elaborate testing suites to determine the most optimal and efficient network protocol for our specific use case in our company. So after deploying the test bed and also the simple client server and also preparing the test suite, I collected a detailed data on connection time and round trip time with varying protocol, payload size, and across both client to server direction and server to client direction flows. After that, I wrote Python script to visualize protocol behavior by analyzing the result log collected, which guided the protocol selection for the next phase. So informed by these benchmark results, we determined the superiority of HTTP3 and web transport in its round trip time, and we decided to move forward with them. We materialized our architecture from high-level system design initially proposed by our manager, and we came up with more concrete and tangible ideas with diagram. While my peer software engineer interns turned this design into a working code, I provisioned Kubernetes resources to host our new backend architecture components. I also modified our GitLab CI/CD pipeline and also the FluxCD deployment for automated deployment to build the new backend components, preparing the infrastructure for large-scale real-time traffic simulation. Well, one thing that would be different from any other system out there would be that the system supported HTTP3 and web transport, which we found superior in the previous phase instead of HTTP1 and WebSocket. And then we moved on to load testing the new real-time backend system using this custom client that I made to simulate thousands of concurrent users and diverse traffic patterns. We also undertook various other use cases, such as international requests. We did SG to US requests, and under both stable and unstable network conditions, where unstable network condition was limited by both its bandwidth and uh, latency, and thus packets were dropped in between. Um, Similar to the previous phases, I then analyze the results by writing Python script to analyze the result log and create visualizations. Currently, we are preparing to present our findings to engineering leads to help decide whether this new architecture should replace the existing systems and determine the next steps moving forward. Through these phases, I faced a range of issues, starting with a misconfigured security groups causing a number of hard to debug network problems. For instance, I had hardship connecting this Vault client inside Kubernetes pod to a Vault server, which was running in an isolated EC2 instance. And it was because a security group rule was misconfigured, and I thus learned the significance of security group in Kubernetes setup, and I would look into security group first in the future if I observe any network being blocked inbound or outbound to Kubernetes cluster. We also faced the phenomenon where benchmarking revealed very inconsistent results due to noisy environment, especially at our home Wi-Fi network. To simulate the actual traffic that will actually incur in the future, we used wireless Wi-Fi to send traffic from our home because office Wi-Fi wasn't that stable. But Wi-Fi itself was inherently, it has instability, especially when we have a burst of traffic during load testing, which led us to adopt tiered testing. I think the most impactful yet interesting challenge uh, was the lack of reverse proxy support for web transport, because web transport is a relatively new technology, new protocol that is rarely used in the industry. There was no reverse proxy out there that was battlefield tested, ready for production. So I solved this problem using going even more low level into L4, UDP based T key port number to IP address mapping using this reverse proxy called FRP, which stands for fast reverse proxy, and was written in Go. I wrote my own FRP cluster manager that monitors how new endpoints are registered or any existing endpoints are dead and automatically adjust the mapping. And more recently, I encountered concurrency and network bugs in our client and server, especially when using Web Transport socket in Golang's Go routine, which forced me to deeply debug race condition, connection state mismatches, and I/O bottlenecks and coroutines. So, all in all, I think this internship allowed me to go full stack, not in the traditional web dev perspective full stack, but from cloud infrastructure at the very high level, high abstraction level, to protocol level and network level, very low level behaviors. I think I've become more confident with tools like Kubernetes, Terraform, Helm, and Vault. And I have worked extensively with EKS, IAM, VPC, Route 53, and numerous other AWS services. I've become familiar with most recent network protocols, including HTTP3 and Web Transport and Quick. And I also have to admit that I became very familiar with low-level network socket programming, basically because I had to work with Web Transport a lot and for debugging purposes. Most recently, I've learned how to debug concurrency and network issues at a much deeper level than I ever had before. And I also have to mention that I've learned a lot about testing, especially system testing, how we should design test cases to eliminate variables as much as possible, how the results should be analyzed to obtain valuable insights, and how load testing should be conducted. Beyond technology, I learned to clearly communicate progress and blockers, especially when the solution wasn't really obvious. Working in a mostly self-directed team taught me to take initiative, reaching out to DevOps team, web team, and mobile team, and manage timelines amid unexpected blockers. The combination of autonomy and accountability really sharpened how I should work in a fast-paced team. So right now, our testing phase is basically done, and we're preparing for a critical presentation to the core engineering team. Depending on the feedback, we will refine the parts of our architecture and assess whether it's really ready for to power production grade services for Verifit and how the transition is going to happen in the future if that is the case. Well, looking back, I started with a very high level description of the system and now have helped bring that vision to tangible life. I tested, deployed, and now evaluated it. Some of the best lessons came from failure, such as broken infra, flaky benchmarks, and race conditions. But at the end of the day, I'm really grateful to my mentor, Ryan Lim, and my peer intern teammates, Darshan and Ryan Lowe, for creating a space where I could take ownership while having the support to grow. So this concludes my presentation. Thank you for listening.